In this lesson, we're going to look at how different intermolecular forces lead to different physical properties of ionic and molecular compounds. So as a recap, before we get started here, the different intermolecular forces, so we can have London dispersion forces, which are the weakest forces between nonpolar molecules. We can have dipole forces between polar covalent molecules. And we can also have hydrogen bonds, which are a special type of dipole forces, which are stronger between a hydrogen and a nitrogen, oxygen, or fluorine. And then ionic compounds, there is no difference between the intra or intermolecular forces. So when we look at melting or boiling points, we are looking at changing from a solid to a liquid for a melting point and changing from a liquid to a gas for the boiling point. So there are forces holding molecules together in solids, so where they can't move past each other. There is movement of the particles in that they vibrate back and forth, but they cannot move past each other. And then when we overcome that force that holds the particles together in a solid and to get to the melting point, then we still have a force that holds the particles near each other, but they can now move past one another once they become a liquid. So those forces have to be overcome at the melting point and the boiling point. So for each substance, the amount of energy or the temperature required to overcome the force where particles can't move past each other, that would be the melting point. And then the amount of energy or the temperature at which particles for a particular substance can now move completely away from one another would be the boiling point. So the stronger the forces are, the intermolecular forces between neighboring particles, the more energy that is needed to break that force holding neighboring molecules together, which means there will be a higher melting and boiling point for those substances. So when we have hydrogen bonds between between polar molecules that have a hydrogen that can bond to an oxygen, a nitrogen, or a fluorine of a neighboring particle, that is the strongest type of bond. And so those are going to have higher melting and boiling points than substances that are also polar covalent, but are just dipole forces in between them. So they don't have a hydrogen and a nitrogen, oxygen, or fluorine. And then the easiest ones to break are London dispersion forces, which happen between non-polar covalent molecules. And we've talked before that the intramolecular forces are stronger than inter, so it's harder to break the bond within a molecule, and that ionic bonds are the strongest type of intramolecular. And also that in ionic compounds, there's no distinction between intra and intermolecular. So ionic bonds are the strongest bond that we can have. Then we have polar covalent bonds and non-polar covalent bonds. So those are all intramolecular. And then we move to intermolecular, and the strongest is a hydrogen bond, then dipole, then London dispersion. So because of that, ionic compounds have forces holding them together that are stronger than intermolecular forces for molecular compounds. And so they are going to have much higher melting and boiling points. So if we look at these compounds, methane is made with 4 carbon hydrogen bonds, and the delta En for each of those 4 bonds is 0.4. The carbon hydrogen bonds are also completely equally spaced, and so the that very slight bond dipole, the 0.4, which isn't enough to make it a polar bond, would cancel out anyways. And so methane is a non-polar molecule, which means that it is going to have London dispersion forces as the strongest type of intermolecular. So that's the weakest type of force, which means that neighboring methane molecules are not going to be held very tightly together, which means not a lot of energy is required to move from a solid to a liquid and then from a liquid to a gas. Hydrogen and fluorine here, that is going to be, I believe, ionic. So we have 4 for fluorine as the electronegativity, and hydrogen, I believe, is around 2.2. So that is over 1.7. So that is ionic, and that is the strongest type of force we can have. Here, the force between all hydrogen and fluorine ions is equally strong. And so that is going to require a lot of energy to break the force between neighboring particles and move from a solid to a liquid. So those are going to have very high boiling and melting points. And phosphorus and bromine, there we need to look up the electronegativity. So if we quickly check the periodic table, oops, wrong one. So phosphorus is 2.2 and bromine is 3. So 3 minus 2.2 is 0.8. So we have a polar covalent compound there. And we don't have oxygen or nitrogen, oxygen, fluorine. So in this case, this is going to be a polar covalent molecule with dipole forces. And so this one was ionic. So when we look at the relative strengths, we have the lowest boiling and melting points would be methane, hydrogen fluoride or hydrofluoric acid would be the highest, and phosphorus tribromide would be in between those two. Okay, solubility. So solubility is the ability to dissolve in water. And we've looked at water before, and the shape of it means that it is not symmetrical. So the bond dipoles that get created between oxygen and hydrogen do not cancel out, and that creates a slightly negative or partially negative region around the oxygen and positive around the hydrogens. And that property of water is incredibly important for life. So that allows a lot of things to dissolve in the water that is in our bodies. So whether that is in our blood, for things to be able to travel around easily. So because water is polar, both ionic and polar substances are likely to be able to be soluble or to dissolve in water. And it is the polar nature, so that slightly positive, slightly negative sides of water that are created that allow other ionic and polar substances to dissolve in water. Non-polar substances are insoluble in water, so they are not going to dissolve. So we can use, once again, the intermolecular forces to help us determine if something is going to be soluble or not. So anything that is ionic or polar, because of that positive and negative region that gets created, those are going to be soluble, and non-polar is not going to be soluble. And that just has to do with the attraction between the positive and negative. So if I have sodium chloride, so the bond between the positive sodium cation and the negative chlorine anion is very strong. But once sodium chloride is put into water, these can separate because of the attraction to the positive and negative regions of water. So if we wanted to separate sodium and chloride, a lot of energy would be required. And so it's a very high melting point to take solid sodium and get it to become liquid sodium. And then again, even higher to go from liquid sodium chloride to gaseous sodium chloride. However, when we put it in water, because of the positive and negative ends of water, the sodium chloride can dissociate, and the sodium will be attracted to the negative area of the oxygen, and the chlorine would be attracted to the positive region of the hydrogen there. Electrical conductivity, so this is the ability of a substance to allow electric current to exist within it. So for electrons to move along. So a substance can conduct an electric current only if an electron or ions can move independently from one another. So that means in a solid where things can't move past each other, there can be no conducting of electricity if ions cannot move past one another. So in metals, which are solid, their electrons can move independently from one another. So in ionic compounds, because ionic compounds have very strong forces holding them together, they require a lot of energy to move from a solid to a liquid, which would allow the ions to move. So when I have a piece of solid iron, there the electrons can move. But if I'm looking at an ionic compound like sodium chloride, here the electrons are not going to move because we have two different ions created. So we have had a movement of electrons from the sodium to the chlorine, and now that attraction that is created from the positive and negative anions is so strong that those are going to be held together. So when I have just a metal, so if I just have a metal piece of iron, there my electrons can move along, but here there's already been a movement of electrons, and now they're being held in place with the attraction between those two ions. So in an ionic compound, we cannot conduct electricity when that compound is a solid. We can conduct electricity when it's a liquid, but we've talked about, because the forces are so strong, a lot of energy or a very high temperature is necessary for that to become a liquid. But we also just looked at solubility. And so when sodium chloride is placed in water, then it will dissolve or dissociate. So the sodium and chlorine will actually separate from one another and be attracted to the water molecules. And then there can be shifting and movement between different water molecules there. So when ionic compounds are liquid or aqueous, which means that they're dissolved in something like water, then electricity can be conducted, because then we can have movement of the sodium and chlorine ions. Molecular compounds cannot conduct electricity because their electrons are shared, and so they're not able to move freely. So even when we have polar covalent bonds, even when it's very polar, the electrons are still being shared. So even though they might be pulled closer to one of the atoms, they are not free to move. So molecular or covalent compounds are not able to conduct electricity. So here's a summary chart of the different properties we talked about. So melting point for ionic compounds are incredibly high because the forces in ionic compounds are very high, so very strong. So we need a lot of energy to break that force that holds two neighboring compounds together as a solid, not being able to move past each other. In a molecular compound, it is much lower. And there's a distinction as well between nonpolar molecular compounds and polar molecular compounds. So the weaker the forces, nonpolar molecular compounds have London dispersion forces, and so they will have a lower melting point than nonpolar. So think about something like oxygen, which has a delta En of 0. So completely nonpolar bonds, nonpolar molecule, and at room temperature, Oxygen is a gas. Water, on the other hand, is a polar molecular compound, and at room temperature, that is a liquid. So we need more energy to pull those molecules apart. Electrical conductivity. So ionic compounds have no conductivity when they are in a solid state because the ions are not free to move. In a liquid state, so whether that is because they are aqueous, they are dissolved, or they have been heated to the point where they are liquid, there is electrical conductivity. In molecular compounds, at no point is there electrical conductivity because electrons are shared and not free to move. And consistency of a solid, so ionic compounds are very hard and brittle. Molecular compounds, so this is, remember, as a solid. So when they are solids, they're soft, they're waxy, they're flexible. And solubility isn't on here, but ionic compounds are soluble. So the positive and negative cations allow them to dissolve in polar substances like water. And for molecular, polar substances can dissolve in water, but non-polar substances cannot dissolve in water.